Now this topic which I'm starting, which is compressible flows, this is basically chapter 9 of our book, and we'll be covering up to section 9.6. So the parts later than that will not be covering. That is, now what do we mean by compressible flows? Compressible flows mean that flows where density of a fluid has an appreciable change during the flow, which means that density is equal to constant is not applicable. So what is the first thing which comes to mind when I say density is not applicable? Density is constant is not applicable. Which equation do you think we need to modify? The continuity equation. So one of the first things which we immediately think is that now in this flow continuity equation, we have to look at the general form. Del dot V is equal to 0 is not valid. Now physically, when we see this, if we look at flow of liquids, we need a pressure drop or pressure change of about of the order of 1000 atmospheres, so that the flow can approach in liquids. It will be difficult, or change of density occurs under much harsher conditions. But in gases, if the pressure drop or if there is a pressure ratio of 2:1, can make the flow approach the speed of sound, and which will make it become compressible. Now, what has speed of sound got to do this will become clear by the end of this lecture. Okay. But what we find is that there are two effects mainly. In compressible flows, there are two effects which are not observed in compressible flows, and there are two of these things which we will find in compressible flows, which we don't find when density is constant. And the first of these we refer to as choking, and the other one as shock waves, which again we will explain as we go through this topic. In choking, what we find is, suppose there is a tank and there is a pipe connected to this. If you want to create a flow in the pipe, how do you create that? You reduce the exit pressure. If you reduce the exit pressure, the flow from the tank will start flowing in a pipe. Now you keep on reducing the pressure, and that is where you see the ratio of the pressure will come in. There's an inlet pressure, there's an exit pressure. Now what you find is, if the Mach number in the flow, now because the flow speed increases, the velocity of the flow increases, and as you reduce the pressure further and further, you will expect the velocity to keep on increasing. Now what we find is, once the velocity, assuming this is one-dimensional flow, once the velocity approaches the speed of sound, you reduce the pressure, keep on reducing, it will become equal to the speed of sound. You reduce the pressure further, it will become greater than the speed of sound. So you will expect the flow rate which is coming out of the nozzle to increase. But what you find is, once you reach Mach number 1, after that, even if the Mach number in this thing increases, the flow rate which is coming out will not increase. That means within this converging tube, you can't achieve a Mach number bigger than 1. Even if you lower the pressure, which will create Mach number 1, if you lower it further, what will happen is the flow comes out at the same mass flow rate. And outside, there is some sort of a disturbance where the pressure reduces from its exit value to the one which you have created. And this phenomena is called choking, which we don't expect in incompressible flows. Now what happens is, as the velocity increases, initially the incompressible assumption is valid. But as the flow speed becomes more and more, incompressible assumption is not valid, and then we have to look at the equations which we are seeing. The other effect which we find in compressible flows, particularly flows where Mach number is bigger than 1, is a phenomena what we call as a shock wave. In a shock wave, what we'll find is, the flow is suddenly moving with some speed, and then there is a region of discontinuity. Across a very thin region, you find the density and the pressure will increase considerably. That means up till this region, till before this region, you had a certain value of rho and P, and within a epsilon distance along x distance, you will find the pressure and density to increase suddenly. And this epsilon distance, what I'm calling, is what we refer to as a shock wave. And this, once again, we will show follows our equations. We can define all these things, we will be able to show all these from our equations of motion for one-dimensional flow. We will look at the simple case of one-dimensional flow. We will not do compressible flows in 2 or 3 dimensions in this course. We'll just follow these simple things. And so these are things which we don't expect in incompressible flows. But these phenomena happen to come here. So now, let us look at our equations in incompressible flows. What we had was, for incompressible flows, that means in these, density was constant, so its value was known. There was a continuity equation. There's a momentum equation, and together these equations gave us the value of V and P. So far what we have seen, we found the values of velocity and pressure from continuity and momentum equation. Density was constant, and we did not do this, but if we want to find the expression for temperature, we will get that from the energy equation. And here what we find is, the energy equation this equation will contain In incompressible flows, because density is constant, what we'll get is the energy equation is a separate equation for T. Energy equation contains density, velocity, pressure, all these terms. But the equation for velocity and pressure does not contain T. So therefore the equations are decoupled. So we can first solve for velocity and then solve for temperature. But this will not happen when the flow is compressible. Now, as opposed to this, when we look at compressible flows, I think I wrote the wrong equation there, plus. I should probably correct the starting thing. I think I wrote that something wrong. Please correct this. I think I made a mistake here. It should be del dot rho v. At the first page of the lecture, I wrote it as rho times del dot v. With that, it should have been capital d rho by dt, not small. So this has to be corrected in the first page also. And here we have del dot rho v is equal to 0. So now what happens is, एनर्जी इक्वेशन हमने किया ही नहीं, कब से आया क्या? जब से समय चल रहा है, जब से आदि काल से, जब से समय चल, तब से टेम्परेचर एनर्जी इक्वेशन में ही है. हमने किया ही नहीं है तो मतलब ठीक है, तो कब से आया क्या मतलब? Since the equation of energy was first derived, it always contained a temperature. We did not do this in this course. So therefore, so now let's see. If we look at compressible flows, we have this, you could treat this as an equation for density. We have one equation, or see, this is one equation. Then we have, I'll move down. Then we have the momentum equation, which will contain V and P, and we have the energy equation, which has an extra variable T. So now if you look at it, you are short of some variables. See, because density is also a variable, pressure, velocity, temperature. So total, if you count 1 scalar, 2 scalar, 3, 5 and 6, there are 6 variables you have, not counting mu, because mu also depends on temperature and flows. Where temperature changes, that will also come into picture. So we have 6 variables, and we have got only 3 plus energy is a scalar equation. We have not done that, but it is a scalar equation. So totally there are 5 equations. So you will need one more equation with these variables. And the final equation which we get, and that is when we talk of, so the, there is an extra equation which is needed. And for gas flows, we get it from the equation of state, which you have seen in thermodynamics. If we assume that the gas is an ideal gas, then I can use P is equal to rho of T. So the extra equation which we will get, which relates P and rho through temperature, will be this equation. Then if temperature changes are important and pressure, then we may also need equation for mu as a function for temperature and pressure. Normally changes with mu in pressure are very low. Main effect is mu with temperature. And this we may have to prescribe another law. Sometimes it's called Sutherland's law of viscosity, which we use. So this again will have to be given. Because now we keep in mind that the flow as it is going, its temperature is changing, its density is changing, and they are changing by big amounts, not very small amounts. So when they change, we have to account for those. So that means now obviously life becomes more and more complex here. So what we do is, because this comes, let's start with a brief review of thermodynamics. And we will assume ideal gases. You are doing a course on thermodynamics, isn't it? How good is it? अच्छा course है क्या? नहीं, दुखी हो गए. No, but what all have you covered in the, you've done the ideal gases and all. First law, second law, enthalpy, internal energy. You get nightmares of these or no? Itna bura nahi. I don't know. What symbol do you use for Cp upon Cv? K or gamma? K. Okay, good. We'll also use the same symbol. So we'll use K for Cp upon Cv. So once again, when we talk of compressible flow, we'll assume we are talking of gases. And the gas we'll have in mind is air. So we'll talk of basically all problems will involve flow of air. It could be helium or nitrogen or carbon dioxide, anything. All you'll have to do is change the values of K, etc. But otherwise, so first thing we do is we know this, there's a ratio of specific heats. What is Cp, what is Cv? Cv is specific heat at constant pressure, and Cv is specific heat at constant volume. And for air, K is equal to 1.4 and P is equal to rho RT. We assume it's an ideal gas, and we also have a relation R is equal to Cp minus Cv, which is a constant. So now in real gases, K, Cp, Cv change with temperature, but in ideal gases, they are constant. So we will assume ideal gas and we'll assume this to be a constant. Now here R, which we have written, R is equal to R universal divided by molecular mass of the gas. R universal is a number which is valid for everything. It's 8314 joules per kilomole Kelvin, and M is the molecular mass of the gas. And for air, R is equal to 287 meter square per second square Kelvin. K is equal to 1.4. We have this relation Cp upon Cv is equal to K, and Cp minus Cv is equal to R. So therefore we can work out this Cv turns out to be equal to R divided by K minus 1. This is in terms of number, it is 718 meter square per second square Kelvin, and Cp is equal to K times R by K minus 1. So this becomes equal to K times Cv, which is equal to Now for constant values of Cp and Cv, we have a relation change in specific internal energy which is equal to U2 minus U1 is can be written as Cv times T2 minus T1 and change in enthalpy which is equal to H2 minus H1. This is equal to Cp times T2 minus T1. And in case if Cp and Cp are not constant, then in fact I should probably put specific this thing, so I'll use a symbol hats here. Then change in specific enthalpy is equal to integral Cv dt and change in enthalpy is equal to integral Cp dt. So this is, I'm just sort of writing it from your thermodynamics course. I'm not teaching these to you. I hope the details of these expressions have been done by Professor Ravi when he taught you the thermodynamics course. Who Ravi is teaching it? Talukdar sir. Now we also define a process called an isentropic process, and when we talk of a reversible an adiabatic, what do we mean by adiabatic process? Process in which there is no heat transfer with the surroundings. And if the process is reversible, reversible means it's a slow change is taking place so that it can come back. If it's a sudden change, it's not a reversible process. Then for a reversible adiabatic process is also isentropic, and in which there's another thermodynamic property which is entropy, and for this process delta S is equal to 0, where S is the entropy. Now we have the first, from first end second law of thermodynamics. They will lead us to T times dH is equal to dH minus dP upon rho for a reversible process. Okay. So this we can write TdS is equal to Cp times dt minus dP upon rho. And for rho we can write P is equal to rho RT. For rho we can write P upon RT. So what we get from here is ds is equal to Cp times dt upon T minus R times dP upon P. And when we integrate this, we get integral from 1 to 2 ds is equal to and this gives right to S2 minus S1. The change in entropy is equal to Cp times log of T2 upon T1 minus R times log of P2 upon P1, assuming Cp is constant. This is for ideal gas. And this we can also write in terms of Cv. This becomes Cv times log of T2 upon T1 minus R times log of. Now these two are identical equations. You can probably use the equations we have done. P is equal to rho RT to get these things. And then also relation between Cp and Cv we had worked out. So from there you will be able to get this relation. So these are basically just some things which are a recap from the thermodynamics course. And from here what we get is, this is the change in entropy, and if we have an isentropic process, in an isentropic process, S2 minus S1 is equal to 0. So once you put S2 minus S1 is equal to 0, then you can find a relation between P2 upon P1 and T2 upon T1 and rho 2 upon rho 1 and T2 upon T1. So then what you will get for that is, and you get this relation from thermodynamics, P2 upon P1 is equal to T2 upon T1 to the power of K by K minus 1, and this is also equal to rho 2 upon rho 1 to the power of K. So these are what you get for an isentropic process in this, okay. So from here what we get is that we can find the relation how pressure, temperature and density are related to each other. Now how this will come in a flow field is that we will look at flow in a small channel of varying area, and there we will see how as pressure changes what happens to temperature, what happens to density, and then using our relations of equilibrium or this thing we will apply this to the equation for velocity. So that is what we will do. Let's see that now how to go about doing that. So here what we'll start off with the, so having seen this review of thermodynamics, what I'm going to do is let me now talk about speed of sound. Because, and speed of sound, this is the rate of propagation of a pressure pulse of infinitesimal strength if I create a pressure disturbance in the flow. I create a very small pressure disturbance. The rate at which this disturbance moves, if there is a still fluid, let's talk of this room, I create a small pressure disturbance by speaking. So now this pressure disturbance travels with a finite speed in the still fluid, and the rate at which this pressure disturbance moves is what we call as the speed of sound. And for this to be the speed of sound, the pressure disturbance has to be infinitesimal. That means even a smallest pressure difference which is caused, what is the speed at which it travels in a quiescent fluid? That is what we want to find out. So now let's see, what we do is consider a pressure wave moving with a speed c in a still fluid. So I show a small thing, small disturbance, which I call as a pressure wave. This wave is moving in a still fluid. If it is moving in a still fluid, let us say the pressure, so this is a wave which is traveling like this. Upstream of the wave, this has not so far affected the fluid, pressure is P, density is rho, temperature is T, and the speed of the fluid here is 0 because this is traveling in a still fluid. And because once the wave crosses this, it will create some disturbance. So let the pressure change which comes in because of the traveling of the wave, let it be P plus delta P, rho plus delta rho, T plus delta T. So once the wave travels, so these changes are caused in the fluid because of the wave. So to analyze this, what we do is we choose a control volume which encloses the wave, and this pressure wave, this is traveling with speed c, which we want to find out. Now we choose a control volume which encloses the wave. So that means we'll choose a small control volume, a rectangle type of a control volume, just consisting of the wave. Now because the wave is moving with a speed c, if we want to make the flow steady, what do? We make our control volume travel with the wave. See, we have seen this before. If there's a boat traveling in still fluid, if we place ourselves on the boat, the entire scenario becomes steady. So what we do is, we choose a control volume which encloses the wave and it travels with the wave. So control volume is attached to the wave, and the reason we do this is to make the flow steady. So now in this control volume, which is now, so now what we have done is, this wave is now steady. The pressure is still P, density is rho, temperature is T. What happens to the velocity in this control frame? Earlier the velocity was 0, but now because we are in this frame, the velocity becomes equal to c in this direction. And here if we look at it, this is P plus delta P, rho plus delta rho, T plus delta T. And what happens to the velocity here? It was delta V. So in this frame, the velocity becomes equal to C minus delta V in the I direction. It is delta V in this direction, to that we add C, so it becomes C minus delta V. Initially it was delta minus delta Vi. So now if we choose it like this, now we carry out now this is our control volume, so we carry out a mass balance. So let's say this area is A. So what does mass balance tells me? Rho times C times A is equal to rho plus delta rho times C minus delta V times A. Okay? So whatever is the mass coming in is the mass going out. We are just assuming a 1D control volume, a very, very thin control volume. So from here what we get is rho CA is equal to rho CA plus delta rho CA plus minus delta rho CA and minus delta rho delta V A. एक टर्म, चार टर्म्स ही तो होंगी। एक मिनट, कौन सी गलती हो गई? थर्ड टर्म इज सेकेंड टर्म, एक मिनट रुको, रो सी ए, रो सेकेंड टर्म इज रॉन्ग। यार क्या हो रहा है? Let me start. I'll do each term again. I'm getting a bit confused. Rho C A. Then I have minus rho delta V A. Then I have plus delta rho C A. And then I have minus delta rho delta V A. Okay. So from here what I can get is, what I've written here is, so rho CA and rho CA will go away, and I have rho plus delta rho times delta V is equal to delta rho times C. Okay. So from here what I can get is the change in velocity which is happening in the fluid will be equal to C times delta rho by rho plus delta rho. Next we will apply the momentum equation. C is the velocity of the wave. Sum of forces on the control volume is equal to m dot times. Now if I draw my control volume here like this is rho, this is C, this is, and this pressure is P, this is rho, this is C, rho plus delta rho, C minus delta V, and pressure is P plus delta P. So therefore what I will get here is P times A minus P plus delta P times A. This is equal to m dot, which is equal to rho AC times V out. V out is C minus delta V minus C. So this is what the momentum equation will give me. M dot, I've taken m dot common. This is how what we have done earlier also. So that gives me just a rho AC, and V out C minus delta V minus C, and this is equal to this thing. Now again A and A will cancel out, and from here what we get is, this simplifies to delta P is equal to rho C times delta V. So therefore from here what we get is delta P is equal to rho C times delta V. In delta V I put in the earlier term, I get C times delta rho upon rho plus delta rho. This is substituting from continuity equation. We get this. So from here what we get is an expression for the speed is equal, in terms of the variable, is equal to delta P by delta rho into 1 plus delta rho upon rho. So this is for a general wave of a general pressure disturbance. Now what we say is, in case if the wave has infinitesimal strength, which means the disturbance is minimal, then delta upon rho will approach 0. And the speed of the wave will become A, which is equal to the speed of sound. And so from here what we get is A square is equal to so this term will become 0, and c will become equal to the speed of sound. So a square, if we call the speed of sound as a, then a square is equal to delta p by delta rho. That means if a disturbance is traveling, whatever is the pressure change it creates, it is traveling in a still fluid. The pressure upstream was P, pressure because of its disturbance of it following is delta P, P plus delta P. So that change in pressure divided by the change in density, in the limit this becomes very easy, is equal to the speed of sound. So what we have is a square is equal to partial, sorry I have written that wrong, it should be partial, I have put in the wrong symbol here. A square should be equal to partial P by partial rho. Now, when we say partial P by partial rho, the question is which variable do we keep varied, which variable do we keep constant? Because it's a partial derivative, and actually here a historical mistake was the same formula had been derived by Newton, and when he talked of the speed of sound, he got it as partial P by partial rho, but what he assumed was that as the wave was moving, the whole process was isothermal. That means temperature did not change. So Newton calculated the speed of sound by taking partial P by partial rho at constant temperature. And he got an answer, and that answer turned out to be about 20% in error. And the reason why that was in error was that the actual wave, when an infinitesimal wave moves, it moves in a reversible way. And it does not exchange any energy with the surroundings. So therefore this partial P by partial rho which we have to consider here when this wave moves, it is not an isothermal process. If you measure the temperature change, it is appreciable. There is some temperature change which is not negligible. But what it turns out is, it is an isentropic process. So therefore this A square, which turns out to be partial P by partial rho, so the correct variable to be kept constant in evaluating partial P by partial rho is entropy, as the process is closer to reversible adiabatic. So therefore speed of sound in a gas is equal to partial P by partial rho with at constant entropy. And as I'll not write this down, but Newton made this error, and so now for an ideal gas we can easily work this out. For ideal gas, A square is equal to K times, where does this K come from? A square is equal to partial P by partial rho at constant S, and this turns out to, so A is equal to for an ideal gas, if you calculate partial P by partial rho at constant entropy, this is equal to kRT. So therefore, for a perfect gas, speed of sound A is equal to square root of kRT. So this is how one works out, and let's say for air at 20 degrees centigrade, A is equal to 340 meters per second, and if we go to a height of 15,000 meter, temperature there is something like minus 156.49. I'm just copying these numbers, and there you get A is equal to 294.39 meters. So it changes with temperature, but it goes like square root of temperature, of the absolute temperature. And even at very high heights, it just goes down to about 300 meters per second or so in that. Now for solids and fluids or liquids, there is a property called K, which is called the bulk modulus. This again you may have seen, and what we can show is A is equal to, I am calling this capital K, square root of capital K by rho, or square root of B by rho, where B is the bulk modulus. Of course, we will refrain ourselves only to gases. So in the next class, I'm going to continue from this. But somewhere it gives you an idea where, when we talk of density changes, we get speed of sound. And that speed of sound basically comes from this relation, partial P by partial rho. Square of that is equal to, or A square